The tree that has at most, or the maximum we can say, at most only the two children. Such type of tree is called as binary tree. When it comes to the complete binary tree, all the leaf nodes should be at the same level. That is called as complete binary tree. Pre-order means root has to come first. Post-order means root has to come at the end. And the in-order means root has to come in the middle. Hello everyone, welcome to yet another session on data structure using C for second semester B.Ca student. In this particular session, we'll continue the discussion on unit 3, that is trees as a data structure. Myself, Indu J, Faculty of Computer Science Department, Vidhyaashram First Grade College, the Temple of Excellence, MYSURU. Let us continue the discussions on tree. In the last session, we have discussed what is tree, what is node, edges, and the different terminologies what we use in the tree data structure. In today's session, we are going to discuss about the binary tree. What is binary tree? The tree that has at most, or the maximum we can say, at most only the two children. Such type of tree is called as binary tree. It can have 0 children, it can have 1 children, or it can have 2 children. It is not allowed to have more than 2 children. Such type of the tree is called as binary tree. When we have 2 children, 1 children is for the left and 1 is children for the right. One is left child and 1 is right child. Either it should have a right child, it should have both a left and right child, or it should not have anything. Such type of a tree representation is called as binary tree. Let's go with the definition. Binary tree is a special type of the tree data structure which every node can have a maximum of 2 children. Is known as a left child and another one known as a right child. In a tree which every node can have a maximum of 2 children is called as a binary tree. That's what we have represented. Either it can have a 0 children, it can have a 1 child, or it can have a 2 children. So this is how we are going to represent. How many children the node, that is node A, which is a root node, will be having root node having only 1 child, which is a left child, right? But here you can see it is having 2 children. B node is having D and C as 2 children. So that is having both the left child as well as a right child. Here we don't have any child, so 0 child. Here we have a 2 child, here we have a 1 child. Here also 2 child, 0 child, and here 1 child. Right? So this representation is known as binary tree representation. There are different subcategories in the binary tree, or we can say type of binary trees are there. Let us see what are the types of binary tree. We have a strict binary tree, complete binary tree, almost complete binary tree, and expression tree, and binary search tree. We can categorize the binary tree into 5 different groups. One is strict binary tree, complete binary tree, almost complete binary tree, expression tree, and then the binary search tree. What do you mean by strict binary tree? Strict binary tree means the node, each node should have 2 children only. Each node should have 2 children. 0 is also not allowed, 1 is not allowed. So that case we call it as strict binary. Strictly the binary tree should have only 2 children. Every node should have exactly 2 children or no children. That means every internal node have exactly 2 children. That is called as strict binary tree. Okay, how do we represent? Here A is having 2 children, that is B and C. So B is having no child, so it is allowed, right? It should have 2 or 0. Now C is having 2 children, allowed. F and G is having 2 children. If I have something like that I here, so this is not the strict binary tree. This is not allowed. Either there should be no children, or it should be have 2 children. Such type of representation in binary tree, we call it as strict binary tree. Okay, you can have here one more example. We have 2 children, again 2 children, again 2 children. Here also I can have again 2 children, 1 and 2. Say consider 1 and 2. This is also allowed. Okay, so this is what the example for strict binary tree. Well, coming into the complete binary tree. What do you mean by complete binary tree? It is also the variation of the strict binary tree where every node can have 0 children or the 2 childrens. Okay, but all the leaf nodes should be at the same level. Getting it? All the leaf nodes should be at the same level. Here in the previous example, we have this extra leaf nodes. What is a level? Level 0, level 1, level 2 and level 3. The leaf nodes are at the level 3 as well as the leaf node are at the level 4. In the strict binary tree, it is allowed. When it comes to the complete binary tree, all the leaf nodes should be at the same level. That is called as complete binary tree. In a binary tree where each node can have a maximum of 2 children, but the strict binary tree, every node should have exactly 2 children or the 0 children in the complete binary tree. All the nodes must have exactly 2 children, and at every level complete binary tree must have 2 children or the 2 nodes to it. It should complete in the single level. All the leaf nodes of the tree should be in the same level. That is called as complete binary tree. Next, coming into the almost complete binary tree. What is almost complete binary tree? Here, what we have here is it is allowed with the one more variable. It can have 0, 1 or 2 children. Such type of binary tree is called as almost complete binary tree. Okay, then what comes with the expression tree? Expression tree will be operator is at the node and it will be having the operands here. So this type of tree representation is called as expression tree. We'll discuss the binary search tree. The element what we put in the binary tree should be in the sorted order. Then we call it as binary search tree. So next what we have is left screw and the right screw. The tree that grows in the left direction, that is called as a left screw. Okay, left screw binary tree. BT stands for binary tree. Left screw binary tree, and the trees grows towards the right direction is called as right screw binary tree. Okay, we can grow. This is an example for almost complete binary tree where we have only 1 children towards the right, and in the left screw where we have only 1 children towards the left. This is a right screw and the left screw binary tree representation. So how we can represent the binary trees or the trees in the form of array as well as in the form of linked list. As we have seen the different data types where we are representing stacks and queues and linked list in different forms, queues as well as in the linked list. So tree can also be represented in the memory block in the form of array or in the form of linked list. There are 2 ways of representing the trees. So let us see how we are going to represent the tree in the form of arrays. So what we have 2 examples here. This is example 1. This is example 2. We have one binary tree. How we are going to represent that binary tree in the array format? First, we have to take the root node at the index 0. Root node should be at the index 0, right? What we have the root node? Root node is 1 at the index value 0. This is representing the index value. This is representing the data or the information that we are storing in the nodes. Okay, Then after root, we have to represent the left child of the tree at the first index. Left child of the tree. What is a left child? 2 is a left child that has to be represented at the next index level. After that, what we have to represent? I have to represent the right child of the particular node, root node, that we have to represent, which is a value we have in the right child, that is 3, that will be represented in the next index value. After this, what we have to do? We have to come back again to the left tree, or we can say that we have to consider the left subtree. We have to consider what? Left subtree. In the left subtree, what we have? We have a left child again. Now this will become a root. We have to go for the left child. That 4 will be represented in the next index value. Then again we have to go towards the right child of that node. That is 5 will be represented at the next index level. Like that, again we have to move to the level wise. Right subtree, left child. Right subtree, that is 3, and the left child is 6. Right subtree and then the right child, that has to be represented. This is how we are going to represent in the array manner, that is continuous representation. Here you can see at the node 9, we don't have any childrens. Here also no childrens are there. No child or leaf node. So what we have to do? We have to represent it as a null. Okay, we have to represent it as a null. So this is a continuous representation. We'll take the second example where we don't have a nodes here. We don't have any nodes here, right? No intermediate node, no leaf nodes. Nothing is there. So how we are going to represent? As I told you, we have to take the root node with the index value 0. This is the index value, this is the data. So 1 is a root node that will be represented in the index 0, index of an array 0. Then we have to check what? We have to check the left child in the index 1, right child in the index 2. Now when coming to the left child, we don't have any children's further. Right, so it has to be represented as null. Then go back to the right child, and again you have to check the left and right childrens of that. That is 6 and 7 will be represented. So here I cannot represent 6 and 7. No, it is not allowed. We have to leave the space that is there dedicated for the children of this left subtree. Okay, then so 6 and 7 will be represented in the continuous memory. In the next level, what we have to do? We have to check for the next level. Hence we don't have a root here. We don't have a nodes also here. So how many? For 4 space has to be given as null. After suppose 4 space, that is a 4 node value, we have to represent this 12 and 13. That is 12 and 13 will be represented with the index value 11 and 12. Why this 4? Because for left children will be having 2 childs, and for the right children will be having 2 childs. So that much of the space has been left when we are representing in the form of array. Hope you understood how we are going to represent this tree nodes in the form of array, in the form of continuous memory allocation. Okay, next how we are going to represent in the form of linked list. Array is a continuous memory allocation, so we have to leave the spaces there. So linked list is not such. So it is easy to implement the or represent the tree in the form of linked list. Each node of the linked list will be having 2 fields, but when we are representing a tree in the form of linked list, each node will be having 3 fields. Each node will be having 3 fields. What this 3 field consists of? The first field will be having the address of left child, and this will be having the actual data, and this will be having the address of what? Right child. Right child. Getting it? We'll be having 3 fields in the node. What 3 fields will be having? The first field will be having the address of the left child. The middle field will be having the actual data what has to be stored, and the right field will be having, or the last field will be having what? The address of right child. Okay, this is to represent only the binary tree in the form of linked list, because we have a restriction in a binary tree that each node should have only 2 children. So we can represent like this with the 3 fields of the linked list. Similarly, also we have F is a data what we are storing, B is a one more data which is a address of left subtree that has to be given here, and this in this particular node, this particular first element or the first field will give the address of next. When it is a leaf node, there will be the no address in either the side of the data. There will be the no address in either side of the data. That will be represented as null. If we have this null, we can say this particular node is a leaf node of the tree. So this is how we are going to represent the trees in the form of array as well as in the form of linked list. Next, coming to one more important type of the binary tree, that is binary search tree. I have stated you that what is binary search tree? Yes, binary search tree is a sorted tree. Okay, when we are storing the element, we are storing the element in the sorted manner. Why we have to sort the element? To make the searching easy. That's why we call it as binary search tree. How we are going to sort the element? The tree where the root node is greater than the left child and the root node is lesser than the right child. So whatever the root node we consider, if we are searching for any particular element which is less than this particular root node, that compares, say, have to search 4. That is my key element. That is my key element. Have to search 4. This 4 key element is compared with the root element. Okay, key element is compared with the root element. If it is key element is less than root, then it will search in the left part of the root. If key element is greater than the root, then it will search in the right part of the tree. So that's why we are going for sorted manner. What is a condition to represent or the right binary search tree is that for all the left subtree elements should be less than the root and all the right subtree elements should be greater than the root element. The tree in which all the left nodes are lesser than the root. What is left nodes? All the left nodes are lesser than the root or the parent node, or all the right nodes are greater than the parent node. That is called as binary search tree. Root node should be greater than left and root node should be less than the right elements. So that is what binary search tree is. What all the operation we have in the trees? As we have traversing, we have a pre-order traversing, post-order traversing, and then the in-order traversing. What is pre-order, post-order, and in-order? We have already discussed when we have discussed with the prefix, postfix, and infix expression. Pre means it is coming before the operand. Post means it is coming after the operands, and in means the operator is between the operands. Similarly, here what we are doing, we are dealing with the respect of root node. What we are dealing with? We are dealing with the respect of root node. What is a pre-order tree traversal? In the pre-order tree traversal, what exactly we are doing? First, we are visiting to the root. After visiting to the root, we have to visit to the left child of the root. and after visiting left child of the root, we have to visit the right child of the root. That is called as pre-order. Pre means root has to come before anything. Okay, that is called as pre-order traversal. When we are traversing, when we are searching for the element, so we search with respect to the root node, right? So first we have to do the traversing with respect to the root itself. Pre-order means root has to come first. Post-order means root has to come at the end, and the in-order means root has to come in the middle. Okay, this is about the pre-order. First visit to the root node, then visit to the left child, and then visit to the right child. That is the case in the pre-order tree traversal. Welcome to the post-order tree traversal. What we have to do? First what we have is visit to the left node. Okay. Then visit to the right node, and later we are visiting to the root node. That is a post-order. Root has to become at the end of the traversing position. So that is called as post-order. Post means at the last. Left, right and root is a sequence for traversing the post-order tree traversal. What with the in-order tree traversal? What is a sequence that we can have for the in-order tree traversal? We have to visit left, then go to root, then go to right. This is a in-order tree traversal. Root is in between the two operands. Okay, root is in between the two operand. What is root? Root is nothing but your operator. So that is how we are traversing the in-order tree traversal. First left, root and then right. So you have to keep in mind that what comes with the pre-order, what is a sequence for pre-order tree traversal, what is a sequence for post-order tree traversal, and what is a sequence for in-order tree traversal. What is the sequence for pre-order tree traversal? Pre means root has to come from first. Root, left and then the right. That is a pre-order. In the post-order, left, right and then the root. Root has to come at the end. In order, left, root and then the right. So that is a in-order tree traversal sequence. So let us see how we can write the code, C code for pre-order, post-order and in-order tree traversal. Let us consider the algorithm how we can write for pre-order. All of you know, because when we are discussing with the linked list, we have already discussed how to create the node, right? So we are creating the node with the help of creating node. After creating the node, we are accessing with the help of arrow mark, right? How to access the element in the linked list with the help of arrow. That's what we are doing it. In this, how many fields we'll be having in the linked list? We'll be having 3 fields. Okay, now in the pre-order tree traversal, first what we have to check for the condition? We have to check for the condition whether root is equal to null or not. What does it mean if root is equal to null? There are no elements in the tree. We don't have any data in the tree. So at that time, we are returning back saying that there are no element to traverse. Okay, if this condition is wrong or this condition false, what we have to do for the pre-order? What is the sequence for the pre-order? Root has to come first. We have to fetch the data. First we have to fetch the data, what is there in that data field. Okay, after fetching the data, what I have to check for? I have to check for the root pre-order root of left. What is there at the left root I have to check, and then what is there at the right child we have to check. This is what the algorithm what we have for the pre-order tree traversal. What we are doing here, if you want to represent this particular example in the form of pre-order, how we can write? First what I have to visit? First I have to visit root. What is a root? I have to print that first. Right. Then what I have to visit? I have to visit the left child. I have to print 25, the data of that left child. First we have to traverse to the root node. After root node, we have to traverse to the left child. Then we have to print that. After traversing the left child, we have now this will become a root. Okay, now we have to traverse to the left child of the root, that is 12. Okay. Then we don't have any further nodes here to the 12. So what we have to go? We have to go for the right child of this root node, that is 30. Okay, we have done with the left subtree of the root. Then we have to go for the right child of the node. What is the right child of the node? That is 75, right? 75 is a right child. Once we have visited this, now it will become a root node. So now from root node, where we have to visit? We have to visit to the left child. What is the left child value we have? That is 60. Okay. Once we have visited the left child, this will become a root now. Then we have to visit what? Again the left child of that particular 60. That is what we have is 52. After that, we don't have any further nodes for this. 52 is a leaf node. Then we have to visit to the next right child. That is what we have in the right child. That is 73. Okay. After 73, what we have to check? We have to check with the right child of the root 75. What we have in the right child? We have only one element, that is 85. So this is a pre-order tree traversal for the given example. First visit the root, then left. If no elements are there, then go to the right. Then after completing of the left subtree, go to the right subtree. Then visit to the root, left, then again left. If there are no element, then move to the right. Okay, this is how we are going to traverse the tree with respect to pre-order tree traversing. Well, coming into the post-order tree traversing, what is the sequence of the post-order tree traversing? First, we should go with the left node, right node, and then to the root node. Let us see how we are going to do that. That is a post-order tree traversal. Again, the same condition what we have. If root is equal to null, return by saying that there are no elements in the tree. If it is not, what we have to do first? We have to first check with the left part of the tree, that is a left node of the tree, and then right node of the tree, and then to the data we have to print. We have to traverse with the left, right, and then the data. So coming to the example, how we can represent this particular example in the post order sequence. First we have to visit what? Left. First we are moving with the root node. We are not printing the root node. Then what we have to check for? Left of that particular, we are not printing yet this. We are checking for the left of that particular root node, which is a left of that particular root node, 12. Alright. After printing this, further we don't have anything. That's why we are printing the 12 here. What we have to check? Right. In the right, what we have is 30. Further we don't have any more children's for 30. So we print the 30. Then what we have to print? We have to print 25. Okay, this is done with the left subtree. We have done with the left subtree. Now we have to go with the right subtree. This is a right subtree. Now we are visiting this. No, we are not printing this. Again, we are checking with the left subtree. Yes, it is a root node. No, we are not printing yet. So we are coming to the 52. Now we have to print 52. Then right, that is 73. And then we are going to print root. Okay, we are going to print. Done with the left subtree again. Then we have to move to the right. What we have in the right? That is 85 we have in the right. Then after that, what I have to print? I have to print the root, which is a root for the subtree, 75. We have done with the 25 left. We have done with the 75, which is a right. Then we have to print the root, that is 50. So this is a post-order tree traversal for the same example. You can make a note here. We are starting with the root node, and here we are ending with the root node. That is what the post order and the pre-order tree traversal. Next, how to traverse in the in order. In order means how we are doing. First left, root, and then right. So what we can provide for in order? We have to check with the condition. First, what we have to check? Check for the left node, then have to check for the data, and then we have to give for the right node. Okay, that is a root node. Fine. So now starting with the root, I am not printing root, I am checking with the left node. Okay, in the left node now this will become root, not printing this. Again with the checking left node, what I have 12. Next from 12, which is a root for the 12, that is 25. Then what we are moving? We are moving towards the right. Okay. Then what we have done? We have done with the left part. Now what we have to print? We have to print the root. After printing root, we are moving towards the right. If we are moving towards the right, this will become a root now. Once this will become a root, we have to move towards the left and not printing yet. Move towards the left. We are printing 52. We are visiting 52. Then we are visiting 60. Then after visiting 60, we are visiting 73. We have done with the left part. Then print root, that is 75. And then print the right part of the tree, that is 85. Okay, so this is what the in order tree traversal. You can see the root is in the middle. The root is in the middle. The root is in the middle. Right? So this is the in order tree traversal algorithm. That's all for the types of tree, binary search tree, binary tree and different form of binary tree. Thank you.